Alright, I got a problem word break. Given a string S in a dictionary of strings word dictionary, return true if S can be segmented into a space separated sequence of one or more dictionary word. Okay, note that the same word in the dictionary may be reused multiple times in a segmentation. Mhm. So we are given this dictionary. This is a list of words, leet and code. So we can break this into leet and code. So we return true. Okay, apple, pen, apple. Because apple pineapple can be segmented as apple pineapple, know that you're allowed to reuse a dictionary word. Fair enough. Cats and dog. Okay, now this is interesting. Is it like why this is false? Why can't I have cats, I have and I have dog. Is it like all the words from dictionary should be within it? We have a space separated sequence of one or more dictionary words. Then why did not this not work? Hmm. I could break it into cats. Okay, and then OG. Okay, fair enough. Yeah, it cannot be broken. Fine. Let's look at some of the constants. All strings of word dictionary are unique. S and word consist only of lowercase English letters. Dictionary words are of less than 20. Total number of words in dictionary are less than 1,000. And S or 10th is less than equal to 3,000. Okay. So what do we do? Let us think. Hmm. So we are given these dictionary words. We could convert this list into a hash set just for easy reference. Maximum number of words are 1,000, so it's not like a big hash set. It's fine. So we generate that hash set, and now we walk through this string. How do we walk through this string is the question. I wonder if a try would be a better use case here. I feel like it. Put all the words in the dictionary into a try, and then when you search, you search that way. Yeah, it seems like a more uh, reasonable way to search. But okay, let's say we don't know about try. Then how do we do? So we do a hash set and we search. So it has to be a try only. There is no other good way because there can be multiple of these words in the dictionary that starts with L, and I have to consider all of them, right? And I keep going till at least matching at least one. And if I find where it does not match anything, then I move on uh, to the next. Then basically I say return false right away, or I move on to the next one. Hmm. I mean, for example, here lead would match this. So I'll break, start from, and then I'll check code and code is matching. Now, there could be cases. Let's think of a case where there are two possibilities, but you only take one because that is the one that works. So something like, let's say, simple A, B, C, D, E, F, right? So let's say the dictionary words are A, B, C, A, B, C, D, and E, F. Now, in this case, we'll see that ABC is a dictionary word. At that point, we have two options. Either we keep continuing or we remove this and check the next guy, right? And we have to take both paths because if we take ABC, then we don't find any DEF. Oops. So we then consider that ABCD instead, and then we see EF, right? So to take both the paths, that is clear. But the only thing that is not clear at this point is because it's a dictionary, you need to use a try. At this point, I'm going to go read about try and then uh, continue on this problem. So I'll take a pause here. All right, so I'm back. I have had a read on an article on try uh, and how it is represented. Basically, every node is a character, and um, like this is a better representation where every node is one character and the overlaps are handled as a separate branches essentially. To verify that I've really understood it, I have first picked up another problem on LeetCode called implement try, and then I'll try to solve this one, and then I'll go back to the word break problem. So let's first try this implement try. Uh, okay, let's read. A try, a prefix tree is a tree data structure used to efficiently store and retrieve keys in a data set of strings. There are various applications of this data structure such as autocomplete and spell checker. Implement the try class. So we have to implement all of these functions. Try initializes a try object. You have to be able to, and these are the functions that you want to be able to check. First is insert a word. Second is search for a word. Returns to the string word is in the try, was inserted before, and false otherwise. And boolean starts with returns true if there is a previously inserted string word that has the prefix and returns false otherwise, right? So I have a quick read. Okay, all this is yeah, basic information. So we add a try, we insert apple, we search for apple, returns true, we search for app, return false because it's not a word, but it starts with will return true. Makes sense. Then we insert app and then we search for app, it is a word as well. Right. So, all right. Now let's try and implement this first. Okay, so what are the thing that a try has? So it will have a root node, right, which will be of type try node. So we need to define a class called, let's just call it node, right? What does node have? Okay, how many, what are the different alphabets? It's only lowercase English letters. Fine. So we'll take that as 26. So each node will either have one a children. So array of, let's call it children. We can also call it branches, but okay, children is fine. And uh, this is of size 26. So an array of 26 and a node inside the null, initialized with null. And each for each node, we also need another indication or to indicate that is this an AND of word. So when you initialize a try, you initialize the first node. Okay, so what will try have? Try will have a node which will be called as root. And this try, what it will do is when you initialize the constructor, will just initialize this root. So root equals to new node, which will then create a children array and an AND of word initialized as false. Right, this is good. Now let's come to insert. So how do we insert the word? We start from, so now it's try dot insert, right? So root is always there. Root cannot be null because root is initialized in the constructor itself. So we get root, which is fine. So we want to go from to multiple levels. So word length, right? So n is we have to walk through these many levels. So and we start with node equals to root. Now what do we do? So we loop n times for int I equals 0, I is less than n, plus plus. And what do we do here? So first time we'll check. Okay, let's get the character that you're interested in. Word.caret index. Now, uh, what would be the index of this character, right? It would be in this children array. What would be the index? So it would be this. And now we'll check is this if node dot children of index, if it is null, then we have to not make it null. We do new node and we make it just that's all, new node. And so yeah, so first character is done. Then we move second character is done, and we move to last character, right? We also then have to move to node equals to node dot children of index. We move on to that guy as well. And yeah, and when you come out of the loop, that means you're done. So the last node is the one that you had inserted, or yeah. So this node is the node which was either created or already existed. But in either case, what you want to do is and of word you want to mark it true. So this is how I will insert. Now let's do a search. So we search a word again, same way. So we get the length of the word. We start with root and we walk through the word. I equals 0, I less than n, I plus plus. Okay, just copy this much. All right, so here I get the caret I'm looking for, index, and if it is null, then instead of now this is a problem, so I return hey, this word is not found because it should be present, and then I move to node equals to node dot children of index, and at the end, when all the words are done and everybody is found, I also want it to be marked as and of word, right? Because I'm looking for a exact word. And starts with is exactly similar, except that it can be a prefix, so it does not necessarily have to be end of word. If you find everything, you just return true. And okay, let's run code, fix compilation errors. Okay, it says new node in compilers. Trie.node cannot be converted to trie.node array. Okay. So root equals to new node. Yeah, it's not node array, it's just node. Okay, run code. Word.length cannot find symbol word, line number 51, because we're searching for prefix here. Okay, changes to prefix, just a prefix. All right, submit. Okay, so now we understand how to convert the dictionary of words that we had into a trie. Let's come back to our word big problem. And what we can do is we can just copy this entire code that we need of trie, right? This class trie. And if we want to use a trie, we could potentially just use all this code here, right? And now given a string as a dictionary, so now I know that from this word dictionary, I could just create a trie. So let's first do that, right? So try, what do I call it? I just call it dictionary equals to new try, and I do for each word in list, for each string s in word dictionary, I add it in the try, which is dot insert is the right thing, I think. We're calling try dot insert, yeah. So dictionary dot insert uh, s, yeah. I don't like to call it s, so let's call it word. So for each word in word dictionary, add it in the dictionary here. So now from a list, we move everything to try. All good. Now we'll walk through this string and we'll check all the small substrings, right, of length 1, length 2, length 3, starting from this index till we find a match. And if you find a match, so let's do that. So I equals to 0, I is less than s dot length, I plus plus. What is this? What does this outer loop signify? This signifies the, I would say, the starting position. Yeah, the starting position. Okay, so we don't really know. Okay, let's see. So let's do it some sort of recursively then, or what? So okay, let's call. Now I'm looking for return. Um, let's just call it check. We return and we want to check what this word in this dictionary and starting from this index, starting from index 0, right? Let's do this. Okay, so now boolean check looking for the string s and the dictionary is a try and starting index is, let's call it start. Now what do I do with this information is I first look for a word till I find it, right? Until I find a word. So you know that L is fixed, R is what we are trying to change, right? So int R equals to start, R is less than s dot length, R plus plus. If what is it called? Insert search. If search, okay. If try, which is dict dot search s dot substring from start till r plus 1. So we're checking for a substring in the try, and if it returns true, then there is when there are two cases, either we consider that option because like we saw this case, right? So we found ABC. So either we consider that or we consider another path, right? Which is that we also consider A because ABC, when we do DEF, it will return false. So Boolean check equals to false. Uh, check equals to, for this case, we would do check uh, as tick, but the start would be whichever index I found, which is R. So I will do R plus 1, right? And here, if R is greater than or equal or the equals to s dot length, then we return true, right? In other cases, if it's not matching, then check will remain false. and we just need to find any one combination that works. So we could do this. We could also do, so this is present, then we could just say, hey, uh, and this check is also working, which is what we were calling. So as dict in r plus 1, then we can simply just return true. Right, then I don't need this. So I tried all combinations. So for example, in this case, I will try ABC and I look for the EF, which I won't find. Then I will try ABCD and look for EF, which I will find. So this is good. We tried all combinations here. And then what can I do here? At the end, I return false. Now, I don't know if there can be repeated problems, which is basically I'm calling this, say, r plus 1. Could I be calling this r plus 1 again multiple times? Which could be like if there is a b, c, d, and ef. I know that ef doesn't exist. Like a b, c, d, and then let's say ef, g, h, I, j, right? So there could be a b, c, d, and there could be this other ef, g, h, I, j sort of. So basically, it's possible that I process it differently, and I reach to the same index again and again. So if I've calculated this once, so I also keep a track of uh, which can be just basically I'm trying to do some sort of DP as well here to, if this problem is repeating, then I want to be able to save this guy's information. So I do, this is fine. I can just create a, let's just call it hash set or hash map integer and boolean. And let's call it memoization. So memo equals to new uh, hash map. And now, so this is fine. And if, so we pass this hash map here. Pass this hash map around. And if this hash map contains this, which is um, right, and here also instead of returning true or returning false, let's call it boolean return value equals to false, and we'll be returning this return value, but before this we will be, and here what we can do is we can just break, so, and we can just break, right? Okay, that's some code. Let's fix compilation errors. There is no R, it's start. Okay, this works. Let's do example test cases. All of them work. Let's try this test case that we were thinking of, which was what? Which was, I forgot, but basically A, B, C, D, E, F, G, and like if you try A, B, C, it does not work. But if you try A, B, C, D, it works because EFG is also a word, right? So if you go to ABC, then you're stuck. But if you go to ABCD and EFG, that works. So let's run this code. It works as well. So submit. Okay, all good. Now let's try and understand what's the time complexity. So using a trie, searching a key in a trie is O of key length. And what I'll be doing here, this pre-processing, creating of inserting all the words uh, into the trie, right? So inserting one word into a trie would take how much time? Again, the length of the key. So how many of our words are there times the max length of a word. So whatever n cross m we can say, that is the initial building of trie, and then searching in a trie would take O of the number of basically length of the key that we are searching for, and how many times we are running this. So for every let's go there. For every we are basically going through each character one by one. No, so for every starting point, we are considering all, we are checking for all possible words, right? Could it just be optimized by, could it be optimized in the sense, like I'm searching for each of them, right? Uh, I could return something like, hey, is it a prefix? Because if it's not even a prefix, then searching again is of no use. That could be an interesting optimization. So what I mean is, uh, first I try A, and I don't find a word A, but I find a prefix A, right? And the answer is yes, I find a prefix A. And the other cases, then when I if I don't even find a prefix A, then there is no point in trying AB at all. But okay, that will sort of immediately break. But for a longer cases, there can be slight optimization here. So instead of just searching uh, for the previous guy, I think it's fair enough to basically in the try have return like two things, like, hey, is it a prefix or is it a word, right? So yeah, I think it's a fair optimization. So let's do that optimization. But okay, before that optimization, let's talk about the overall time complexity that we're talking about. So I try for each and every substring. So from A, I try A, B, A, C, A, D, A, E, A, F. I search for all of them, right? Which is how many? Which is the number of N, right? And then with B as well. Well, I won't. Will I try with B even if I find something with A? I mean, worst case, right? So in worst case, I'm feeling it could be like N squared, right? Uh, if N is the length of the string, then it could be N squared. Okay, because I will be trying. Let's see here. Yes, R equals to star. I try each and every combination, and then from B as well. Actually, no, right? I'm not really trying anything. I can't really try anything from B. So I try from A all combinations, and then wherever it breaks, wherever I find a word, I try all combinations thereafter. So it's not really N squared, but still, okay, I don't know how to come to an exact one, but I'll call it N squared just for simplicity. Let's go to that optimization that I was thinking of. So what I was thinking is when I'm doing this search, I can also do search for a prefix. So here the word, basically what I'm saying is if a search does not yield even a prefix, then there is no point in trying for other combinations of R, which I don't know how to. Okay, so in this search, I can do a little bit of change. So this starts with I can get rid of, and search instead of Boolean would return enum. and this enum I can define maybe outside. So one is prefix, another is exact, and so this will return what do I call it? This call is match type. Okay, and this search will here at the end it is so okay, and there is one more thing, none, right? So this will return match type dot none, and based on this will return match type dot, if it's under word then exact, otherwise this will return match type dot prefix. Now what I wanted to do was basically at any point if this search, so we get this search result, right? So int uh, not so match type. So match type is basically you search as dot substring start plus one. Now if what my point was, if is the match at any point you don't even find any match, which is if match type is uh, okay, if then you can just break, right? Because no point in checking for further strings because they definitely won't make any match. And once you find so if this is not the case, then it's either a prefix match or an exact match. If it's an exact match, we move on. If it's a prefix match, then maybe if I look for a further R, then I can get an exact match and I will continue. So this definitely improves efficiency a bit. Let's submit and see if it really helps or not. I mean, other variables and stuff. Okay, so somewhere some mistake. Expected. Mhm. This is fine. Okay, you don't want to call it enum. You want to call it maybe match type. Just to run code to fix first. The double equals to has to be moved. And yeah, so we change this to match equals to match type dot exact. Then you move to the next one. Okay, now submit. So it massively improves the time complexity, at least practically. All right, so we learned about using how try, and then after we learned new about try, I think uh, it was quite straightforward that we go through this to look for matches, and once we find a match, we'll look for a match from there on and so on. And we also talked about even if you find a match, you still have to go and look for further cases because like ABC, like I think it was this case, like here ABC was a match, but then DEF wasn't. But if you look ABCD and EF can be a further match, so we handle that as well. And also the cases like let's say ABDEF, something like that. You don't need, and when you start, you see a let's say ABD. How to explain? So let's say ABD is a word, and ABDF. That's these are the only two words. And when basically when you try ABD, And let's say this is GHIJ, lots and lots, like a big one, right? So once we try ABD, it's fine. Then we will try next, and we won't find anything. When we try ABDE, we don't find it as even as a prefix match. Because we don't even find it as a prefix match, we can just break at ABEF. Don't have to keep on searching each of them again and again and again. There is no real point of doing that, which is the extra condition that we added to know whether it's a prefix match or not. All right, so that's for this one.